The sensors employed in this work are chemoresistive, so they change their resistivity as a function of the gas concentration. The active material of our sensor is made up of metal oxide semiconductors. This material is synthesized under form of nanoparticles in our laboratories. These sensors are made up of three parts. The first one is the active material, that is this white square, that is made up of metal oxide nanograins. The second part is the substrate, that it works as a mechanical support of the sensor, and the third one is a heater that is placed on the bottom side of the substrate.
Figure A shows the sensor semiconductor film printed onto the substrate, connecting the two comb-shaped gold electrodes. The sensor is bound to a TO39 socket with golden wires. Figure B shows the heater, a platinum meander, positioned on the substrate's backside. Some of the equipment of the sensor laboratory and of the clean rooms of the University of Ferrara. A screen printing machine is used for serigraphic sensor film deposition in Figure A. All thermal treatments are performed in a dedicated oven in Figure B. Clean sample handling is performed under a chemical hood in Figure C.
The sensors are realized here in the sensor laboratory, and in particular are assembled with the bonding machine by thermocompression. The material used in this study are metal oxide based on tin oxide materials.
Since these sensors are based on semiconducting materials, it is very important to characterize them electrically and thermally by using the ED curves and Arrhenius plots respectively. Usually, these characterizations are made by using very huge laboratory instrumentations. For this purpose, our solution is represented here. This is a very portable device able to characterize one sensor directly on field. In order to evaluate the device potentialities, it was tested with two sensors. One based on tin oxide, and it is used as a benchmark. And the second one is based on tin oxide with addition of 1% of gold. To evaluate the potentialities of the device, it was tested with two different sensors. One based on tin oxide material, and it is used as a benchmark. And the second one, it was a sensor based on tin oxide with the addition of 1% of gold nanoparticles.
The new device is entirely controlled through touchscreen views. Sensor heating is shown in Figure A, sensor film voltage feeding is shown in Figure B, the Arrhenius plot is shown in Figure C, and the current to voltage and sensor output are shown in Figure D. The average Arrhenius plot generated by the device for tin oxide is shown in Figure A, while the one for tin oxide plus 1% gold is shown in Figure B. The plots resulted in being independent of the film voltage. For clarity, the positive or negative standard errors are represented by the two red and gray lines above and below the average ones in Figure A. The device also generates the average current to voltages for the tin oxide plus 1% gold sensor shown in Figure A, and for the tin oxide one in Figure C, voltages were recorded ranging from 0 to 10.4 volts in 1.04 volt steps at the working temperature of 350 degrees Celsius, as was their linear fitting. Conclusions. The user-friendly device introduced here was able to rapidly test and calibrate two representative tin oxide type sensors in dry air. The device precisely calculated and set the desired sensor working temperature, and it acquired and plotted the sensor Arrhenius plots and the current-to-voltage relationships on a touch screen. The Arrhenius plots, automatically performed at different film voltages in dry air, demonstrated the independency between sensor conductance versus temperature and the film-applied voltage for both sensors. The current-to-voltage relationships of these sensors were almost linear with a negligible hysteresis effect at all three selected temperatures and for long-lasting voltage applications. The gold addition increased tin oxide conductance and enlarged the Arrhenius plot plateau region without any alteration to the current-to-voltage linearity. Finally, this study showcases the suitability of tin oxide-based sensors when employed in applications where film conductance linearity is required at different working temperatures, independently of the duration of the applied voltage.